So y hat, which is y dot u over u dot u times u, is called the what of y onto u. Orthogonal projection. Orthogonal projection of y onto u. All right, what must be true for this set of three vectors x, y, and z to be an orthonormal set? Yeah, they have to all be perpendicular, and they all have to have unit vectors. They all have to be unit vectors. For an orthogonal set, they just have to be all orthogonal. Orthonormal set means they have to be all normalized to the unit vector. So you could say x dot y has to equal x dot z has to equal y dot z. Those all have to be 0, because that will tell you that it's orthogonal. You could also write they're all orthogonal to each other. That's fine. And they must be normal vectors. That's fine. That's an additional thing. The length of x has to equal the length of y, has to equal the length of z. All have to be 1. Sure, you can have half. Yeah, if you forgot the length part. So this says they're all orthogonal, or each pair of vectors is orthogonal. And this says they're all unit vectors. So if you did it in symbols or words, that's fine. Okay, an M by N matrix U has orthonormal columns if and only if U transpose U equals the identity. All right, so my notes for today's class are pretty extensive. It took me a whole page just because there were a lot of definitions, right? So I had to write them all down, plus the theorems. All right, so the definition of an orthogonal set just means that every pair of distinct vectors in the set is orthogonal. So you have to make every possible pair. When you dot them together, their dot product has to be 0. And then we have this theorem that says if S is an orthogonal set of non-zero vectors, so that's key, they have to be non-zero for this to apply, then S is linearly independent. So this one, we use this one a lot in today's class and in your activities. If you have an orthogonal set, it's automatically linearly independent, assuming 0 is not in there. All right, an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. So an orthogonal basis is a basis that happens to be orthogonal. That's just a definition. And then I just have some basic, this is some stuff that we already know, but it leads us to this theorem, right? So if S is an orthogonal basis, because it's a basis, forget the fact that it's orthogonal, because it's a basis, then any y in the subspace can be written as a linear combination of vectors in the basis, right? That's what a basis is. Any vector in the space can be built from the basis vectors. So you can write it as a linear combination like this, C1, U1 plus blah, 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 CP, UP. So usually you would set up an equation, a system of equations to solve for the weights C1 to CP. And we've done this many times throughout the semester. But when you have an orthogonal basis, we have this really fast way of being able to calculate the weights, where each weight is y, the vector y, dotted with u sub j, right, the appropriate vector from the orthogonal basis, over u dot u, where j goes from 1 to p. So you can get each of the weights that way. So we'll do an example of that later. All right, so given a non-zero vector u in Rn, then for any vector y in Rn, you can decompose it into the sum of two vectors. One a scalar multiple of the given u, and the other orthogonal to u. So that sounds like super crazy. Like it took me a while to wrap my brain around it until I read the part about decomposing forces. And I was like, oh yeah, We've done that so many times, or you guys have in physics, right? So typical reason for doing this decomposition is to resolve a physical force into its horizontal and vertical components. But the same process can be applied more generally in any dimension. And the vectors that we resolve into don't have to be I and j, horizontal and vertical. They can be any u and some vector orthogonal to it, right? Because I and j are orthogonal. So you can just pick any u and an orthogonal vector. Yes. Yeah. So yes, you're right. You can't, it's not just any random one. You have to find the one that goes with your u. Yeah. So our goal is that we're going to try to decompose y into y hat plus z. Okay, y hat is going to be a scalar multiple of u. So, and z is the vector that's orthogonal to u. Okay, so y hat is called the orthogonal projection of y onto u, and you compute it using this formula. And there's a very brief proof of where that formula comes from in your text. I won't go through it, but feel free to read it. It's not difficult. And z, from this y equals y hat plus z, z is called the component of y orthogonal to u. And z you just get by doing y minus y hat, right? If you come back up here, once you know y hat, you can solve for z. So it turns out that y hat and z are the same for any scalar multiple of u. So any vector in the span of u will give you the same y hat and z. And we'll do an example where we'll try two different vectors on the same line and see that you get the same y hat and z. And then later I'll have you prove it. So sometimes we call y hat, instead of the orthogonal projection of y onto u, sometimes we call it the orthogonal projection of y onto L, because it's the same for any vector on that line. And then if you want to compute the distance from y to L, it's just the length, the distance from y to y hat, because y and y hat, we built y to be orthogonal to u or to L. So you just have to do y minus y hat. And there's a question, I actually didn't put any questions like this on your lecture or activities today, but there's a question regarding this on your practice test. So you can be on the lookout for that. Okay, so a set is an orthonormal set if it's an orthogonal set of unit vectors. An orthonormal basis is a basis that's also an orthonormal set. The standard basis for Rn, like 1, 0, 0, 1 for R2, that is sort of a simple example of an orthonormal basis. Right? The two vectors are orthogonal and they both have length 1. And then we have this theorem that an m by n matrix U has orthonormal columns if and only if U transpose times U equals I. And I will have you do an example in your activities where you show directly that its columns are orthonormal and verify that U transpose U equals I. Yes? Sure, yeah. So any vector space has an infinite number of bases, but there's only one ortho, that's not true. Scratch that. There's not just one orthonormal basis. Because you could have 1, 0, and 0, 1. You could rotate those two guys like 30 degrees, and you'd still have an orthonormal basis.
Each vector space has one basis.
Nope. Lots of orthonormal bases. So let's think about R2, right? This vector and this vector, I and j, right? Orthonormal basis, because those two vectors are perpendicular and they have length 1. If I rotate each of those, say 30 degrees, right? This still has length 1, and this still has length 1. They're still perpendicular, but it's different basis.
If you find the basis for this of combination, go back up.
Mm-hmm.
and then you take them all so that
Mm-hmm. No.
oh, so it could be any combination of those vectors
Right.
or
Right. Yeah. Okay, so now we have a theorem about matrices that have orthonormal columns. Okay, so if you have a matrix that has orthonormal columns and x and y are vectors in Rn, then if you take the length of u times x, that equals the length of x. So what that says is that the mapping x goes to u of x preserves length. So the length of the input vector equals the length of the output vector. And ux dotted with uy is the same as x dot y, and that says that the mapping preserves inner products. The inner product or the dot product of the input is equal to the dot product of the outputs. And as a consequence of this second bullet, then ux dotted with uy equals 0 if and only if x dot y is 0. Because ux dot uy is the same as x dot y. So this says that the mapping x to ux preserves orthogonality. Okay, so if the inputs were orthogonal, then the outputs are orthogonal. All right, and then the last thing, an orthogonal matrix is a square invertible matrix U such that U inverse equals U transpose. Such a matrix has orthonormal columns and orthonormal rows. And any square matrix with orthonormal columns ends up being an orthogonal matrix. All right, so let's do some examples.
normal orthonormal matrices, like the orthonormal basis onto the
Row, that's a good question. Is the orthonormal basis row equivalent to the identity? Yes. Yes. Yeah. So, yeah, because I and J, if you were to take those vectors and put them in a matrix, you get the identity. That would be row equivalent to these blue vectors. If you row reduced, I believe you would get the identity. I think so. Okay, so we have 3 vectors, u1, u2, and u3, and then a 4th vector, x. We want to show that u1, u2, and u3 is an orthogonal basis for R3. An orthogonal basis for R3. So that means it has to be a basis for R3, and it has to be orthogonal, an orthogonal set. So to show that these 3 vectors form an orthogonal set, you have to show that every pair of vectors in the set is orthogonal to each other. So I have to show that u1 dot u2, u1 dot u3, and u2 dotted with u3. Every possible pairing of vectors, I have to show that all of those are 0. So u1 dotted with u2 is going to be -1 plus 0 plus 1, right? You just multiply respective components and add them all up, and that gives you 0. Okay, check. u1 is orthogonal to u2. And then u1 and u3, when I dot product those, I get 2 plus 0 minus 2, which is 0. Okay, so u1 and u3 are orthogonal. And then u2 dotted with u3, I get -2 plus 4 minus 2, which is 0. Okay, so u2 and u3 are orthogonal. So I know that that set is an orthogonal set. So now I just have to show or explain why it's a basis for R3. So u1, u2, u3 is an orthogonal set. So any orthogonal set is automatically linearly independent. So that was a theorem from earlier in the notes. Okay, so this is a linearly independent set of 3 vectors, and any linearly independent set of 3 vectors is automatically a basis for R3. That's a theorem from a ways back. Okay. So my set is linearly independent. Theorem from 6.2. And any linearly independent set of 3 vectors is automatically a basis for R3, old theorem. So we've shown that it's a basis, and we've shown it's an orthogonal set. Therefore, it's an orthogonal basis. So if I were to normalize the vectors u1, u2, and u3, what kind of basis would that produce? Orthonormal, right? So they're already orthogonal. If I normalize them by making their lengths all 1, that would produce an orthonormal basis. Right, normalizing the vectors means make the lengths 1. All right, so now I want to express x as a linear combination of the u's. I know it's possible because u is a basis for R, the u's make a basis for R3. So any vector in R3 I should be able to write as a linear combination of the vectors in the basis. So I'm going to do this 2 ways. The old way would be I need to take x and I want to write it as a linear combination of the u's. So that I just need to know what the weights are. So I'd have C1 U1 plus C2 U2 plus C3 U3. And then my x is, of course, I didn't write it down, 8, -4, -3. And then my u's as a matrix, put them all in a matrix. So I've got 1, 0, 1, -1, 4, 1, 2, 1, -2. So those are all my u's, u1, u2, and u3, times a vector of unknown weights. And then how would I solve that for the unknown weights? Row reduce. I'm going to take that U matrix, augment with the 8, -4, 3, and row reduce. I'm not going to finish it. You guys know how to do that. Okay, so now from a theorem in today's section, I can actually find the weights in an easier way, right? So my notes say that each weight C sub j is equal to y dotted with u sub j over u sub j dotted with u sub j times, that's it. Those are my weights. Okay, so C1 is going to be, or I should have said x there. That's the formula for a general y. We called it x in this problem. So x is going to be 8, -4, -3, dotted with u1, which is 1, 0, 1, over 1, 0, 1, dotted with itself. So this becomes 8 minus 3, which is 5, over 2, 5 halves. So there's my first weight, C1. And then C2 is going to be my y, 8, -4, -3, dotted with U2, because I'm trying to find C2. So it's -1, 4, 1, over u2 dotted with u2. So that would be -8 minus 16 is -24, minus 3 is -27, over 1 plus 16 is 17, plus 1 is 18. So that's -3/2. And then one more. C3 is going to be my x dotted with u3, which is 16 minus 4 plus 6 over u3 dotted with itself, 4 plus 1 plus 4. So it's 18 over 9, which is 2. So there are my weights. So that means that if I RREF this guy over here on the left, I should end up with, you can check it later if you want, 1, 0, 0, 0, 1, 0, 0, 0, 1, 5 halves, -3 halves, 2. You did it out. Okay, good. So you get the same thing either way. Again, when you're doing it by hand, it doesn't feel like this weight calculation is any easier. But if you're programming a computer, it takes a lot more steps to RREF a matrix than it does to just do some quick calculations. Yes. Uh-huh.
Where you're trying to construct the vector x.
Mm-hmm.
You construct the vector perpendicular to, like when you're trying to construct the vector L, would you use some trig there to get your two vectors to construct x from your basis?
Yeah, I think you could. I think if you were trying to do this sort of geometrically, you could draw it and use some trig to figure out what the y hat and the z are. Yep, that's in the previous section. Yeah. All right, let's look at number 2, and then I'll give you some problems to do on your own. All right, so I want to compute the orthogonal projection of y, which is 1, 7, onto the line through u, which is -4, 2, and the origin. And then we want to write y as the sum of two orthogonal vectors, one in the span of u and the other orthogonal to u. That's, I want to write y as y hat plus z. All right, so the orthogonal projection of y onto u, or y onto L that contains u, is y hat is y dot u over u dot u times u.
Well, because the line goes through that u.
Mm-hmm.
Either goes to the second.
Sure. Yeah. How do we know that this will end up on that line?
Well, on which side?
Oh, that's a good question. We don't until we calculate it. Because it just has to be any, no, because there's only one way that'll work. There's only one multiple of u that'll work for this, and this is the formula you use to get it. We don't know where on this line it will end up until we calculate y dot u over u dot u. That's your multiple of u. Okay, so y dotted with u is -4 plus 14, which is 10. U dotted with itself is 16 plus 4 is 20. And I have to multiply that by the vector u, -4, 2. So that's a half times -4, 2, which is -2 1. So there's my y hat. So it turns out to be in the second quadrant.
Right.
Yeah.
I just really noticed.
Mm-hmm. Yep. All right, and then z, right? So that's the first part of the question. We found the orthogonal projection of y in the onto u. So it's negative 2, 1. And then z is the part, the orthogonal component, right? So z is just y minus y hat. So my original y is 1, 7. Y hat I just calculated as negative 2, 1. So I get 3, 6. So I can now write y, 1, 7, as the sum of a vector in the direction of u plus a vector orthogonal to u. That's the second part of the question. So negative 2, 1 is in fact in the same direction as u. It's in the span of u, the multiple of u. And 3, 6 is orthogonal to negative 2, 1. And I could check that by dotting them together, right? Did I indeed find the vector in the orthogonal direction? Yep, because their dot product is 0.